Hello friends, today I am going to discuss optical waveguides and guided modes. To understand the waveguide concept in optoelectronics, it is very much important to understand the phase. So let us start with this. Suppose we have sin theta, y is equal to sin theta, and we need to plot this. This is y and this is theta. Means this axis is sin theta, and you know it's sinusoidal like this. So this side is angle, this is pi by 2, this pi 3 pi by 2, and this is 2 pi, and then it repeats. So all these angles are called phase. So when we have phase angle pi by 2, we have maximum. When we have phase pi, we have zero value of this function, and when we have phase 3 pi by 2, we have its minima value -1, and when we have phase 2 pi, we have again zero value. So phase is nothing but the angle of sinusoid. It is sine wave or cos wave. Angle always is called the phase. And why it is important in EM field theory? Because electromagnetic field is written as E is equal to e to the power j omega t minus kz. Here this is exponential form, complex form, so its real part is the actual wave. So when we take real part, it's written as sine of omega t minus kz. So at the place of theta, here it is omega t minus kz. So this theta, or we can write phi also. Phi is equal to omega t minus kz is called the phase. This omega t minus kz whole part is the phase. So whenever electromagnetic field propagates in space, so this z coordinate changes. So when z coordinate changes, its phase will change, and whenever time passes, so this t coordinate will also keep on changing the phase. So phase changes by these two parameters z and t. Suppose we have this plot again, and this phi is nothing but omega t minus kz. So how to analyze this? First, suppose we have dropped z. So at any constant z we want to see, from origin at some point z is fixed, and we want to see how phase is changing. So if this term is dropped, phi is nothing but omega t only. And what is omega? Omega is equal to 2 pi f. So what is the frequency of the electromagnetic field? With that frequency, it will keep on oscillating. Why? Because this omega t is linear. Phase is linear with respect to time. So phase will linearly increase as time increases. So phase will keep on changing from 0 to pi by 2 to pi, then 3 pi by 2, and then 2 pi, and keep on increasing, and hence the electric field amplitude will also keep on fluctuating from 0 to maxima, then 0 again minima, then again 0, like that. So as time changes at any fixed point in the space, the electric field magnitude will keep on changing as the phase changes. Why phase is changing? Because time is changing. Now suppose we have fixed the time at some fixed time, say t is equal to t naught. This term is not going to change. Then phi becomes function of space z. Then what happens at any fixed time? If we want to see, suppose this is z direction now. So phi is function of kz, and k is constant. So this direction is proportional to z now. So at any fixed time, if you want to see what is the phase here? It's different. So as wave propagates, because wave propagates with some velocity, so at different time it's having different position. So at different position in space, phase will be different because phase becomes function of z. So we just want to analyze how phase is changing with respect to space. When I am fixing the time coordinate at some fixed time, we want to see what is the phase at here at different position in the space. So what happens? Again, it's function of z. So at what is the phase then? Kz. Simply magnitude of phase becomes kz with respect to space. Generally, in optoelectronics, we need to see this type of thing because at any fixed time we want to see what is the phase of electromagnetic field, and it's nothing but phase is nothing but k times z. What is k then? K is called the propagation constant and it is given by 2 pi by lambda, and this is in free space, but if it is in some medium, okay, and any medium, it is 2 pi by lambda, n is divided here, so n becomes here, n is the refractive index. Next very important point is the polarization. So what is polarization? Suppose we have this electric field. So we have three dimensions. This is z dimension, this is x, so x cross y is equal to z. So z will be this direction, or say this is x coordinate, this is y coordinate, x cross y is equal to z direction. So suppose this is magnitude of electric field. At the same time, electric field can be in different direction also. Suppose electric field in y direction, it will be like then this. So whenever one field propagates in z direction, it can be perpendicular to, it can be in x direction or it can be in y direction, fluctuating in. So whenever it fluctuates in one direction, it is called one type of polarization, and if it fluctuates in another direction perpendicular to propagation direction, it is called another type of polarization. So there is two types of polarization, TE and TM, transverse electric and transverse magnetic polarization. Suppose we say this is parallel to waveguide, this axis, and this is called TE, transverse electric. If electric field magnitude fluctuates in y direction and y is parallel to waveguide, then the polarization is called transverse electric polarization. And when this x direction is perpendicular to the waveguide, then it is called TM polarization, transverse magnetic polarization. So there are two types of polarization. One is both are perpendicular to the direction of propagation. So we have understood the term phase, polarization, and now let us understand the term interference. Suppose we have two field, electric field at different phase. Suppose this starts at this zero phase and goes on changing in this direction, and suppose this starts with some same phase, zero phase, and it goes. So both are with the same source. So both are having same phase position. So at this position both are in zero phase, at this position both are in pi by 2 phase, at this position both are in pi phase. So then if these two adds up, these two meets at some point in this phase, then it constructs, its magnitude will keep on increasing, so its magnitude will increase like this. So this is called constructive interference, and whenever there is opposite phase, suppose another is going like this, so when it is in zero phase, this is also in zero phase, this is in pi phase. Why we'll say this is in pi phase? Because it's going downward direction. This is in pi phase, so this is also in pi phase. So this is in zero phase, this is in pi phase, this is in pi by 2 phase, this is 3 pi by 2 phase. So always phase always remains pi. Phase difference always remains between these two pi. Then the sum of these two is 0 always. So this is called the destructive interference. Whenever there is completely pi phase difference between two waves, then their sum is always 0. So this is called the principle of interference. And whenever there is phase difference between 0 to pi, if phase difference is between 0 to pi, then there will not be complete 0. When this 2 will be added, there will be some different pattern. Now let us understand the concept of waveguide. Let us now understand the waveguide. So in waveguide we will understand the what is planar waveguide. Suppose we have this one plane above this, another plane between this, another third plane below this. So, or you can say the medium. One medium is above this plane, one medium is below this plane. This plane is perpendicular to the board. Suppose this is my board, white board, and this is one plane perpendicular to this white board. Another plane is perpendicular to this white board, and between these two there is another medium, and outside there is another medium. So this medium is called the planar waveguide. When we will launch light within this, it may be confined within this, and there will be a 3D waveguide also. Like suppose this is my 3D structure and we are drawing this. So this is 3D waveguide and this is 1D, 2D planar waveguide. So these both all are called planar waveguides. This is two-dimensional planar waveguide and this is three-dimensional planar waveguide. Now let us understand the concept of critical angle or total internal reflection. Suppose this is N1, this is also N1. Say this is N1 and this both side is N2 refractive index. So this is of one type of material, this outside is of another type of material. And suppose the light is going from this within this medium and making angle theta with the perpendicular normal. So there will be something reflected back, something going outside. And because there are different types of medium, Snell's law will work and we can write N1, say this is theta 1 sine theta 1 is equal to N2 sine theta 2, and this is angle say theta 2. And what happens, this theta 2 will not be equal to theta 1, and this is the law of transmission. Both will be scaled with the N1 and N2, because N1 and N2 are not same, there will be some beam bending, so beam will bend. And how it bends, if we will keep on increasing this angle theta 1, it will keep on bending, and at one time what will happen, suppose this is one angle, it will completely graze the surface. So this angle is called theta c, critical angle. So when it becomes N1 sine theta c, then this angle becomes 90 degrees. So sine 90 is equal to 1. So sine theta c is equal to sine of theta c is equal to N2 by N1, and theta c is nothing but sine inverse N2 by N1. So this is the critical angle, and whenever light is launched within this medium above this critical angle, what will happen, the light will be completely returned back to the same medium, and this phenomena is called the total internal reflection. So suppose angle is, here I am launching at some angle theta, and such that theta is greater than theta c, then this will be completely reflected back in the same medium with same angle theta, and this phenomena is known as total internal reflection. So condition is that theta incident angle must be greater than the critical angle. Now if incident angle, so this is greater than critical angle, what will happen, a light launched at this angle will be totally internally reflected from this surface, and again from this surface it will be totally internally reflected, fulfilling this total internal reflection, and from here again it will be. So if this is N1 and these two are N2, what should be the condition? N1 must be greater than N2, because sin theta c, we saw theta c, sin theta c must be equal to N2 by N1. So N1 must be greater than N2 for having some real value of critical angle. So a medium which is having higher refractive index, light gets confined within that medium. This is the very much important concept. Suppose there are 2, 3, 4, 5 mediums, and one medium is having the highest refractive index, and we are launching the light. Light will pass through all the mediums, but when it reaches the highest refractive index medium, it will get confined within that medium. It will not come out of the medium, because total internal reflection will help the light to get completely confined in that medium which is having the highest refractive index. So what is reflection coefficient? Let us understand, this is medium N1 and this is medium N2, and light is launched at some angle theta. So some portion will be transmitted, some portion will be reflected out. So this is say incident, this is ET transmitted, and this is reflected by ER. So the ratio between reflected by incident is called the reflection coefficient. So R is called the reflection coefficient, and this was given by the Fresnel. So this is called Fresnel reflection coefficient. At some angle theta, it is defined as N1 cos theta 1 minus N2 cos theta 2 divided by N1 cos theta 1 plus N2 cos theta 2. But this equation is for one type of polarization. Say this is for TE polarization. We can say R TE. Why TE polarization? For TM polarization, this equation changes, and derivation you can understand in the book Sedeku. So what is TE and TM polarization here? So light is propagating in this direction, and suppose this is Z direction, there will be two more coordinates direction here. So suppose this is X direction and perpendicular to this is Y direction. X is coming outward, Y is going there, and Z is going in this direction. So whenever electric field is in this direction, parallel to this plane, this is T polarization, and whenever electric field direction is coming outside, this is TM polarization. So for T polarization means electric field is parallel to this waveguide plane in Y direction, then it is called the T polarization. For that type of field, reflection coefficient is given by this equation. For TM polarization, let me write that equation also. So for TM, if I am writing R TM, and what happens? These two changes here, N1 becomes N2 and N2 becomes N1. That also. Just you can write this also. So RTM will be equal to N2 cos theta 1 minus N1 cos theta 2 divided by N2 cos theta 1 plus N2 cos theta 2. You can get it. It's a derivation from the book Sedeku Electromagnetic Field Theory. Let us understand now what is guided mode. Guided mode. So this is a planar waveguide or 2D planar waveguide. This is N1 refractive index and this is N2 at outside. You can say this is made up of silicon. N1 is equal to 3.47 and both sides there is air. This is also air 1. This is also air is equal to 1. So this type of waveguide forms a 2D planar waveguide. Now suppose light is there inside like this. So when it propagates, it will keep on changing, fluctuating left right. So this is the zigzag motion of the light within the waveguide. Now suppose this is at z is equal to 0 and this is at z is equal to say z naught. So if I'll ask question, when it gets transferred from this direction at 0 phase was 0, when it comes here, that is z naught, what will be the phase? How to find this? If we know the answer of this, we will come to know the guided mode, concept of guided mode. So let us start this question in mind, how to get the phase. If you will say will keep on, what is the general way of getting the phase? It's nothing but phi is equal to kz. K is the propagation constant and it can be known by knowing the wavelength. So if wavelength is given, we can find, and in some medium there will be n also multiplied 2 pi n by lambda. So if wavelength of light is known, we can find the k, and if the propagation distance is known, then we can find the phase. So in propagating from this point to this point, we have to calculate all these distance, zigzag motion, and wavelength is very much small. Say wavelength is 1.55 micrometer, lambda is equal to 1.55 meter, and this distance is suppose 500 micrometer. Then there will be infinite fluctuations within this length. So how to get sum of all these lengths? Then only we will be able to multiply, and then we will say phase, what will the phase is here. So it's very much tedious work to know all this distance propagated. Then we have to acquire some different way. Now suppose wavelength of light is lambda, then k naught will be 2 pi by lambda, and within this material k will be equal to 2 pi n by lambda. So this is nothing but k naught, so k naught into n. So k inside the medium is nothing but k naught into n, where k naught is the propagation constant in the free space. So here we are writing cannot is n1 is nothing but the propagation constant within this medium. So with this cannot n1, it's propagating. What is this? Propagation constant beta, you can say beta, or cannot n1. K is equal to cannot n1. Now this is going at angle theta with the normal. So we can break this vector into two different directions. So suppose in this direction, z direction, its component is equal to k naught n1 sin theta 1, and in vertical direction its component is equal to k naught n1 cos theta 1. So the wave is propagate while going in this direction, it goes some in this direction also, in this direction also. So it's the vector sum of this two direction wave propagation constant, and it's equal to this and this. Now we have buckets. This direction we say kz, and this direction we say ky. So this is equal to ky. So in y direction ky, and this z direction is the kz, and kz is equal to this, ky is equal to this. Suppose the height of this waveguide is h. So whenever it starts going in this direction, comes back, again reaches here at the same position. It starts from here, get totally reflected from here, again get totally internally reflected from here, and reaches here at the same axial point. So this is called one round trip. Within one round trip, in this vertical direction, it goes two times. It goes up, comes down, and here again here. So it travels 2h distance. So what is the phase accumulated in this direction, y direction? So in y direction, propagation constant is ky. If we multiply ky into 2h, because the propagation phase in y direction is nothing but propagation constant in y direction multiplied with the total distance. So this is the phase accumulated in y direction in one round trip. So this is called round trip phase in perpendicular direction. And what is ky? It's the cannot n1 cos theta 1, and we are multiplying 2h. So 2h cannot n1 cos theta 1 is the phase accumulated in perpendicular direction. Now upon reflection, there is another again phase change, because it's happening here and it is happening here, total internal reflection. So while light goes TIR, total internal reflection, there will be phase change always. So this phase change at the upper level is called the phi u, and this phase change at the lower level is called the phi l. So we can add two more phases here, plus phi u plus phi l. The question here arises, why phi u and phi l? Why at total internal reflection there will be some phase change? It means whenever light is going at the, suppose here it is launched at zero phase, while reflecting it will not be in the same phase, zero phase. There will be some phase difference. It may be 30 degree or 40 degree phase will be changed while reflection. However, there is no propagation distance. At the same point it's reflecting back, still there is some phase change on reflection. Let us understand why, where from it comes. While light going totally internally reflected, at some point, at the same point, there will be some phase change. Let's understand that concept. Before discussing why phi u phi l happens, let us understand this, what I have written in previous. Phi y is the round trip phase, total phase change in the this transverse y direction in one round trip. So one round trip is called, if light is going from this point to again reaching the same point, what happens, this light will interfere with this, because both are in going in same direction, so both are the parallel now. So this is going this direction, this is going parallel, so these two light will be interfering when both are in same phase. So if this total phase change in the vertical direction, which is called the round trip phase, is some multiple of integral multiple of 2 pi, then there will be constructive interference, and these waves will sustain within the waveguide. The concept is, whenever the round trip phase in this vertical direction, because in vertical direction there is reflections, phase keeps on changing here. In this direction there is no change of medium. In this direction medium is changing. So we are going to calculate total phase change in one round trip, and this wave will sustain within the waveguide when this total phase change is the multiple of 2 pi, because constructive interference happens when the phase is the multiple of 2 pi. So this equation is called the phasor equation. Phasor equation, and in this equation phase is nothing but function of theta. You can see theta 1 incident angle, height of the waveguide, so this is the height of the waveguide, and n1 is the refractive index of the waveguide, and the wavelength also lambda. So total phase is nothing but a function of angle, launch angle theta, height h, refractive index of the waveguide n1, and the incident wavelength of the light lambda. Based on this, at some, suppose we are fixing this waveguide height n1 and lambda we have fixed, then for some certain angle of theta 1 it will make 2 pi phase change. So if m is equal to 1, so m is equal to 1, it corresponds to some angle theta 1, and this equation is fulfilled. Now suppose m is equal to 2 and this equation is satisfied for some another angle, say theta 2. Again for m is equal to 3, this equation, phasor equation, is satisfied with some angle theta 3. So what do you say about these angles theta? These all angles must be greater than critical angle theta c. So we will say theta 1, theta 2, theta 3, whatever angles is coming must be greater than the critical angle, because then only there will be total internal reflection. Now only at these angles light will be sustained within the waveguide. What will be the light between these two? Some angle is between these two, say theta 1 less than theta 2, and theta 1, theta 2, theta 3 are the solution of this phasor equation. So if some angle lies between these two angles, theta 1, theta 2, those light launched at this angle will not be sustaining within the waveguide, and those are called the evanescent waves, and these are called the guided waves. The concept is guided wave. So only those waves will be guiding inside the waveguide which satisfies this phasor equation, and those are at some certain angles. So we can say that if this is waveguide, at this angle theta 1, this angle theta 2, and this angle is theta 3. All these waves will be guiding at this angle. So this will form like this will form like this. So path of all will be different, completely different, and those will form the guided modes. What happens between these two? If any light is going, those will not sustain inside, and that is those are called the non-guided wave or evanescent evanescent waves. So this is the concept of guided mode, and now we are in position to understand why this phi u and phi l, where from it comes. So that concept where from phi u and phi l, that is the phase, comes upon total internal reflection, I will discuss in the next video. This video has become very longer length, more than half an hour. Thank you.